Okay, I'm Zach. I'm in the Graduate School of Education, my illustrious colleague here. I'm also appointed 50% in UC Berkeley School of Information. My lab studies cognitive models of knowledge representation in order to understand human learning better, and also studies human learning in order to design better computational cognitive models. So that is part of the main focus of the lab. And in addition to that, based on our observations, what kind of unique pedagogical, instructional, informational user interfaces can we design to create different learning experiences. Dor showed these ants using some form of collective intelligence perhaps, or some physiological feedback network in order to create this bridge. And given that as of late I'm primarily using connectionist approaches to understanding cognitive representation, I'm probably over here in that group of ants, and in activism coordinations maybe over here, but someone needed to be over there to help build that bridge. So I'm not going to be reinventing connectionism, but connectionism has been revisited, especially in its application to natural language recently, in quite profound ways. And I'm extending that to the application to behavior in educational contexts, and I'll get into that. What to expect from this talk? The claim I'm making here is that connectionist models produce a fruitful representation for better understanding emergent cognitive structure, both in contexts that involve motion and those that don't. So that's what I'm asserting, that's what I'm claiming. And to support that, I'm going to give an introduction to emergent semantic models in the domain of language. And I hope by midpoint in the talk, you'll know exactly what I mean by emergent semantics. And then I'll show empirical results from the application of these models to educational contexts. These contexts will include educational contexts that involve no movement, such as to course enrollments at this university and representations of those courses from those enrollments, to fraction problem solving in a web tutor, and then in the category of physiological data, eye tracking with a STEM tutor system that was a collaboration with Martina Rao, who's at University of Wisconsin-Madison, and touch sensors with, of course, well-known MIT P. So the ratio of time I'm going to spend on one versus the other is about 2 to 1. And maybe better understood by some, it's about this much of non-movement to this much of movement. It's a different way of understanding it. Okay. So to the introduction of emergent semantic models in the domain of language. But before I get there, let's do a trace back of the literature that led us there. So Hopfield in 1982, in one of the most cited proceedings of National Academy of Sciences, talked about neural networks as representing features, as being abstract feature representations, and allowing for emergent features to be learned using stochastic gradient descent. Hinton in 1986 talked about distributed representation from those same kind of models, and he depicted distributed representation in this example, where you have about 16 family members represented here in what's called a one-hot form. You see this white square means Arthur is selected, and you can imagine there's 16 possible squares that could fit in there. And then the relationship of mother is selected. And so what happens here, since this is a neural network, Arthur has a bunch of weights that represent a vector, and then they're getting added with the vector for mother. And then you get these activations across all the 16 family members, and the one that has the highest activation is Victoria, which is Arthur's mother. And so Hinton showed that this model could be posed in such a way that mother is this distributed concept throughout the space, meaning any family member plus mother, and you would get that family member's mother, assuming they're in the vocabulary, assuming they're among the 16. And of course, connectionist neural networks have been debated as different representations of cognitive processes as compared to classical graphical representations, which I spent a lot of my PhD work studying. And it's one of its first applications to education. This was not in learning analytics, but was in a medical journal. This was studying how med students go about diagnosing disease and to see if there was local representation in neural networks of the submitted diagnosis to see if one of the neurons would indicate to the instructor that this was an expert or novice making the classification. So they've been applied to education. That was 1996. But okay, fast forward a whole lot of time since Hinton's distributed representation, and you have learning distributed representations from language. Thomas Mikolov has been at the center of this in language, the catalyst. And this idea of distributed representation that was talked about all the way back in 1982 is central to everything that is kind of hot in AI, image classification, AlphaGo, intelligent games, automation, autonomous vehicles. But I'm going to focus on Word2Vec, which is actually not a deep network. It's the shallowest network you can come up with. It's a single hidden layer and it's linear. So what's new? Well, what's new is evidence of emergent semantic representation learned from big data. The previous stuff here showed how these models could accommodate such representation, but now we're actually seeing it emerge because we have the data sets to observe it from, to learn these models from.
What does it mean to have big data? The term is used frequently, but I'm not sure I understand.
I'll show you in the Word2Vec example.
Okay.
Often it means a lot of samples, but when social scientists use big data, they're talking about varied behavioral data. So you could say multimodal data is big data, even if it's not very many subjects. There's debate about that, but I'll show you concretely what it means in this talk. Yeah. So let's talk about distributed representation for a moment, since it underlies all of this connectionist approach. So the words here that are being displayed, you can think of them as vectors extending from the origin. So we have bike, bikes, mouse, mice, goose, geese, toad, toads, item, items. Any pattern you can observe with these collections of words, this collection of words.
Do you want native English speakers or non-native?
Non-native, please. Either one.
Singular, plural.
Singular, plural. What else can we observe about their positionality?
The plurals are lower and shifted to the right.
Okay, so it seems like the plurals have a similar relative relationship to their singular. Okay. So that would be considered a distributed concept, plurality, right? Because it has this same relationship between the singular across the space. So it's distributed throughout the space. And I put in brackets plurality as a concept because plurality, if this is all the words, let's say in the English vocabulary, plurality would not be there. It would be somewhere else. So the literal semantics are separate from the conceptual semantics. The concept is distributed, but it's separate from the literal representations. So what you can do in this space, for example, is say toad plus the plurality vector, which is this average offset from the singular form, equals toads. Goose plus plurality equals geese, just like Hinton's. Family member plus mother equals that person's mother, okay? Right, so plurality is the distributed concept. The other words are the literal words and their vector representations. Haven't said where we learned this from. That's just the basic concept of distributed representation. So this is how the model learns to represent those words in a vector space from what I'm referring to as big data. So here's the first sentence from everyone's favorite Russian novelist. All happy families are alike. Each unhappy family is unhappy in its own way. And what the model does is it sweeps through the entire corpus, and it takes every word in the corpus, and that word will serve as the input at least once, but as it iterates multiple times. So families, let's say, is the input word. Now this model is trying to predict the words before and after families in this context. All right, so it's trying to predict based on families and the vector representation that, let's say, it starts with, predict all happy and are alike, because that's the context window. And you can think of this learner as what people do, let's say when they're trying to figure out MITP, can I predict what's going to happen next? All right? Or a baby interacting with a device saying, oh, what's going to happen next based on what's going on now? Now there is a big difference between those examples in this, the big difference being agency, where those learners can manipulate the input. The input is fixed here, but that's what's going on. The model's trying to be able to make sense of what happened before and what's going to happen based on this context, based on this input word. And so it sweeps across the whole corpus, and it makes these predictions. And if the predictions aren't good, it uses stochastic gradient descent and backpropagation to modify those weights. Say, does my internal representation allow me to predict the future? No, not so well. All right, let's make the necessary changes. Keep going, iterate, 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 until it ends up with a representation that does help it make sense of the world, in this case, the semantics. So Thomas Mikolov, who kicked this type of work off, has worked for Microsoft and Google and Facebook. When he was at Google and he introduced this, he ran it on a corpus of 1 billion words, which were from the Google News archive. Right? They store all of the news that they have on news.google.org to learn representations of each word in the vocabulary.
Sorry, what's criteria for making sense?
Having a representation of words that allows you to predict which words are coming next and which words were previous in this context. That's making sense. Yeah.
Okay.
So maybe a somewhat shallow making sense. It's a very shallow model, right? This is not a deep model. One hidden layer. If this hidden layer were not here, it would be a massive multinomial logistic regression with a vocabulary equal, with the number of categories equal to the number of words in English. Okay, so how do they validate this? Because you could have such a model grow up, and just because it predicts well doesn't mean it has a valid representation of the relationship between words. So how does that get tested? So the way it gets tested is Mikolov and colleagues created this analogy validation set. Sorry, you can't see it very well, which has 13 different relationship types. And then they create examples from each type. So I'll just read out some of these. This is capital world. They have 116 examples, such as Paris to France, city and state. You can imagine what that is. Currency, gender, brother to sister, so opposite gender words. Past tense, plural is one of those. And so what they'll do is they'll take an example test analogy, which is two pairs from the same relationship type, and they'll see if the model can complete that analogy. So it'll say geese, literally the vector for geese, minus the vector for goose, because that gets us, here, this is geese minus goose, right? So we go in the other direction from what this vector would be, and that gets us to the plurality vector, because if you take goose out of geese, you're left with the concept of plurality. And then if you add goose to that, or excuse me, if you add toad to that, what is the closest word to that? And if the closest word is the word that's anticipated, that's considered a hit. And if it's not, that's a miss. So how often do these analogies end up with hits? 61% of the time. I think there's room for improvement there. And that's certainly not the kind of accuracy you see with other stunning, deep net achievements. But remember, the number of categories being predicted is pretty big, 1.3 million words are in this vocabulary. So that's how many possible words could have come out of this analogy. Because it's all words in the English language plus proper nouns and different capitalization of things. They don't do much pre-processing. So what structure is learned? I'll get more deeper into the idea of structure, but what kind of relationships are learned? How do you explore this? So what they'll do is they'll start off that analogy, given an example relationship. They'll say France is to Paris as Italy is to, and they'll ask the algorithm to complete that. They'll say Rome. Here's some other examples of what it said. And it could be, you could say semantic relationships that have something to do with the real world, such as Microsoft is to Ballmer, as Google is to Yahoo. It got that one wrong, right? So that's among the 39% that it gets wrong. IBM is to McNeely, Apple is to Jobs. So you see the relationship. Who passed the SAT here? Okay. So this is an example of how you could explore the vector space based on this analogical mechanism. So to give a better idea of how vectors are represented, they did PCA on just the country capital words. So they PCA'd that down into two dimensions, and you see the country on the left, right, China, Beijing, and you see an imaginary line connected between them. And so this is that distributed representation. This is that offset, right, from one word to the other that represents country and capital. And you can see it's not perfect. So this is why it's not. This is why it's 61%. Is because if you take, let's say, Turkey's vector difference here, and you apply it to France, you're not going to get Paris. You're probably going to get Warsaw. All right, so that's the language part. Now into educational contexts. And we'll start with course enrollments. So what I'm doing here is I'm starting with non-STEM, non-motion contexts to build intuition, and then I will get to STEM motion contexts. Okay, so can emergent semantics be inferred from enrollment sequences the way they're inferred from language? So let me jump back here and show you what I'm considering now to be a sentence. So student took CS 61A, then Math 1B, Spanish 12, statistics. So now instead of words in a sentence, it's courses in a course enrollment sequence. And is there meaning in that enrollment selection? That is, does the context in which you took a course, so the other courses you took at the same time, give meaning to particular courses the way the context of the use of a word in a sentence gives meaning to that word, right? Like I really babeled that movie, I'm going to buy it as soon as it's available. Even if you don't know what babeled means, by context you can infer some meaning to babeled. I liked it, right? So similar, can some semantic meaning be given to courses based on context? Unsubstantiated before the study. Okay, so we looked at the historic data. We learned representations of courses using that same algorithm. It's called a skipgram. We validate representations by way of analogies constructed from prior knowledge about courses. So you will see increasing amounts of skipgram word-to-vex applied outside of language, but you'll rarely see validations of them. And then we explore the semantic space through vector arithmetic, much like Mikolov did in language. And then we allow students to explore this representational space with, through software. And here you see an example now. Vectors are courses. This is info 1, 2, 3. And then this is the centroid for info, which is just the average of all those info school vectors. And then here you can say is the centroid of computer science. And you can say, well, how similar is computer science to information by looking at the cosine similarity between those two centroids. Our data set was 3.6 million enrollments at Berkeley between 2008 and 2015. So lexical relationship pairs like plurality were used for word vector model validation, but what ground truth can we use to validate courses in our vector models? So we had to come up with this. There were two sources of truth that we used. One was course credit equivalency pairs, which is the registrar says that these two courses are so similar to one another that you can't get credit for both of them. So in a space, those should be cosine similar, because the registrar says they are so similar that you can't get credit for both. That's one source of truth. Right? The other source of truth was these relationship categories that we put together, like the plurality one. And those categories look like this. There's honors pairs, Math 1B and its honors version Math H1B, online, my class digital learning environments 161, and its online version W161, and so forth. So when validating for equivalency, we took each of the 381 equivalent pairs and then sorted the courses by their similarity to A, and if B was at the top of the list, it was considered a hit. Otherwise, it was a miss. So the median rank of B in our course to vec model was 18, and as a baseline, we looked to see, well, what if you just created a simple representation based on the catalog description of the course, the text, and not based on enrollment behaviors. And that did better, but not on average. On average, there's a lot of outliers in the bag of words approach, but it was better on average. We've since gotten closer to this, and if you combine the two, you do even better. But in analogies, the bag of word approach does not do well, but the what I'll call course to vec approach does do well. And so let me walk you through some of these analogy validations. We said mathematics 1B is to H1B as physics 7B is to, and then asked it to respond, and it said physics H7B. Let's go to here. Game theory and statistics is to game theory and economics, as linear modeling in statistics is to what in economics, and it came up with linear modeling class in economics. It doesn't always work though. Psychology's introductory course is to psychology's computing course, as statistics introductory course is to, and we wanted statistics 133 computing, but it gave us an honors seminar. The computing course was rank 8. So how well does this do? Out of the 2,200 analogies, when does it get it right? 40% of the time, which is comparable to 61% that Mikolov gets with their 1 billion words. We have 3.6 million enrollments. The better statistic is not how many total samples you have, but how many samples per vocabulary you have. And they only have 1 order of magnitude more than us in that category. So that was the validation of, is the representation meaningful? Did it capture some regularities that have some sensibility to them? Now it's time to explore. What can we learn from this, maybe? So the first step in asking it that question is we took all of the department centers, so the vectors that were the average of all their courses, and because this is a linear model, it is closed to, it has arithmetic and scalar closure, and we did these department additions. And we said, for example, Asian studies plus classics equals what? What department is closest to the addition of those two things? And it says East Asian languages, Asian studies plus religious studies, Buddhist studies. If you're wondering what the School of Information is all about, the model says business administration plus computer science. It's not bad. My favorites are legal studies as rhetoric plus political science. And statistics is demography plus mathematics, which is certainly true in schools that study the census or that started that, which is not Berkeley. Looking at this visually, we took all courses and then measured their scalar projection to the department center. So like what magnitude of that department is that course, does that course contain? So as an example, we plotted every education and mathematics course with respect to the amount of mathematics and education they have. And critical studies and education was the least mathematical course. Now, on the mathematics axis, differential manifolds was the least educational course. And then school curriculum, of which there are 3, was the most educational math class, which has some face validity to it. That's, all right. So you may want to know as a student what the difference between courses are. We have 2 courses here, 140, which is econometrics, and 141, which is advanced econometrics. What's the difference between them? If you look at the catalog, I'll tell you they say the same thing. The underlined words are the only differences. Regular econometrics says application and problems in, and then advanced says statistical theory for and model and its variants with examples from. Which doesn't give you a great idea of the difference between the 2. So let's ask the model. Let's ask the model what the difference between Econ 141 and 140 is, because this course description, the literal semantics that we have about the 2 courses is not telling the story. And the model says Math 110, which is linear algebra. And if you look at the syllabus of both, you'll find that linear algebra is one of the topics that is found in 141, but not 140. Okay, so how did we go from just sequences of course enrollments? That's it. Just sequences of course enrollments to this rich, logical, semantic manipulation where we can say things like the difference between these 2 courses is linear algebra, the concept of linear algebra. How does that happen? I'm asking you, no. One idea is enrollment isomorphisms, which is what I would consider to be the emergent semantics, meaning that these constellations of courses, let's say math 7b and its relationship to 7a, which is a sequence relationship, and its relationship to h7b, has an isomorphic relationship to that same constellation in physics. So that's why that analogy works. So semantics are these isomorphisms. They are these regularities. Now, yes, we have to add things like the name of the course to it for us to interpret it, but those similar constellations are there whether we add labels to them or not. And maybe the adding of labels is a whole other world of effort and how we add symbols to other kinds of representations. What else is it? It could be an aggregation of student course perceptions. Students enroll in these courses, of course, before taking them, based on what they've heard of it. So are the relationships we see some aggregate representation of what they think the courses are about? We know that this is true to a degree when it comes to word vector models. Several papers about word vector models containing implicit bias, scoring very high in implicit bias tests, in fact. Is that a reflection of outdated thinking from past news articles? It could also be degree requirements creating part of the structure. Sometimes students take courses, they don't have a rationale for why they're taking it other than they're told they have to. So that degree structure is sort of the faculty's representation of courses maybe also being inserted into this. And then lastly, distributed representation of concepts. Hinton called it in 1986. And I want to make a note here that Michael's in Michael's presentation, he showed an example of context-dependent learning. And one way to think of context-dependent learning here that doesn't generalize is, let's say if a student only has this relationship of non-honors to honors within their department, right? So that consistency of regularity only applies in the department because they don't care about other departments. They just know that they need to understand that department. They don't need a generalizable vector to represent that. So everything else is kind of not aligned with that. Now, if they thought it was important enough, then they perhaps, if this is an analog for cognitive structure, they would have to realign a lot of things in their representation, right? That takes a lot of effort. So there's going to be this trade-off. Do I want to spend that effort? Is it in my interest? Is there utility to spending that effort to realign my understanding of things so that this concept is now general instead of local? That's one explanation. All right. So I said that part of what the lab does is now generate user experiences. So how do we surface some of these representations to students? We shouldn't have a monopoly on these pieces of information and inferences. So we created something called Ask OSCE out of an NSF grant. It's linked to by Berkeley's official registrar page. And on this page, students can do things like say they only want to look at economics courses, and then they want to sort those courses based on their closeness to public policy and their distance from statistics. And if you could see this, you get a lot of public policy courses within economics, which is just inferred from this vector space. And sometimes it's wrong, right? It was 40% accurate in those analogies. And you can also look at alternatives to courses, right? What courses are most cosine similar to one that you can't take for whatever reason, maybe it's full. Okay. So now let's apply this idea to a math context, a problem-solving context, where the sentences are now your answers to every question in a particular math sequence. Integer multiplication, you answered 5.5. Then you answered a square roots question and answered 8. So the actual answer is the sequence. And it's going to help us with this difficult task. Do these answers share a common misconception or incorrect procedure? Take a second to look at that, because I know some of you are experts at this, like Thomas. Evidence of how hard this is experts take a while to answer this, right? Anyone want to take a guess? Yes. Yeah. Oh, okay. Okay, so yes, they both involve the mistake of adding instead of subtracting, right? So it's 1/3 now plus 5/2 to fill in the value in the box. 1/2 plus 5/6 to fill in the value in the box, right? So they don't subtract. So the objective of the application to this context was, one, to leverage, I'll use the term again, big data, to algorithmically cluster wrong answers by their common misconception or procedure. This is really hard for experts to do. Can data represent that misconception as a distributed feature in the space that we can cluster? And then to design interventions that adhere to guidance from education psychology, which can scale because of if this approach is successful. So better pedagogical affordances online if this works. So it's the same idea. We have the sentences of problem answers. We learn a problem answers representation based on its context. And another intuition for this is that the problem's context is a signature for that misconception or wrong procedure. That something led up to that, perhaps, and something will follow as a result. Maybe the right answer will follow. Maybe it's a very ephemeral state that you're in and you rectify it immediately. But that context will provide a signature that will help recognize some category to that answer. So we looked at 3 exercises, mostly fractions, and they contain between 78,000 and 134,000 learners in a popular web-based tutoring platform. Excuse me, that was how many student answers. It was 21,000 to 36,000 students, learners, we don't know that they're students, and 78,000 to 134,000 responses. So we made 30 clusters of 10 problem answers each, and then hand tagged each of the answers for what we believed as non-experts might be the misconception or wrong procedure behind them. Here's an example cluster. I usually pause to ask what the commonality is here, but I don't know if you guys are good at this task. But for time, I'll give you the answer. And you can't see it, that's also a problem. I'll forgive you that. So the student answered 15 here, but 15 is also the number of triangles that's shown in this preemptive hint. Here, the number of groups of triangles is 4, and that's what the student answered. These are all wrong answers. And then here, the size of the groups is 2, and that's what they answered. So in this group, I would not consider this to be a misconception or wrong procedure, but perhaps a common lazy answering strategy is what is shared between these answers. So when we did the validation of the tagging of the groups, ideally we want the groups to contain all the same misconception tag, to be homogeneous. And they were 46% homogeneous, which is certainly way better than random. But like the analogy validation could do better. Is it successful because of 46? It's publishable and borderline usable. I would say it should be higher than 60 or 70% to be really usable. All right. So what kind of pedagogical affordances are possible? Thomas, in his presentation yesterday, mentioned how a student or multiple students were destroyed by being confronted as being wrong. Oh, that's what you think? You're wrong. That's not true. That was not an effective pedagogical strategy. And many would agree with you. Smith and other colleagues who have been professors here. So Smith pressed for the importance of developing and refining students' conceptions through reflection and discussion rather than direct confrontation, and also pushed that misconception may just be a correct understanding overgeneralized, right? So if you shut down that correct understanding, they may not even be confident that they knew what they really did know, just because they've overgeneralized, right, outside of the appropriate context. So what can we do here? Well, we can take that same question I showed you at the beginning. Student answers this wrong. And instead of saying you're wrong, we can say another student answered a question like this but made a mistake. See if you can find the mistake and fix their answer for them. And what we show them is a wrong answer from the same misconception cluster. Okay? So now they're not threatened by inspecting their own answer. Oh, you think there's something wrong with me? But what is likely wrong with the answer they are inspecting is what's wrong with theirs. And then we do the reflection part. Do you want to change your answer? Okay. So this is a hypothetical design, but we're in the process of putting this into practice. Another possible intervention, Watkins had an inspiring piece where she encourages student voicing of uncertainty as a mechanism to invite peer feedback and addressing incomplete understanding via co-construction. So she'll have a student who's maybe express their understanding, and then she'll encourage a student who looks confused to voice that confusion, and then they have a dialogue. So what you could do here is you could have a student who answered a particular way that was wrong, but then in this vector space, you could say that wrong answer plus what equals the correct answer, and look for a student who answered in that plus what, and then have them start a dialogue. There's probably a lot you need to do otherwise here in instrumenting this, creating some trust. Can't just pair strangers together and expect them to open up about that. But this is a social intervention that would only be possible with this kind of representation. All right, now these are shorter, but now we're getting into physiological data, and we'll start with eye tracking. So here the example is you have the x and y of one eye, say the left eye, taken at 30 hertz. And then you also have interspersed into there tutor information on their performance on certain problems. Problem 1 correct, more eye information, problem 2 incorrect, etc. All right. So this is the context for the second work, which was Martina Rao's chemistry representation tutor. Martina Rao specializes in multiple representations involved in learning. And so here she's testing it in a college course, a real college course, and the students have to use her tool. Here you see the fixation point as students answering this question. We'll wait, I think a multiple representation will pop up at some point. So I'll say right off the bat, this high frequency data stuff is hard. And the results are not as glamorous. But what we did find is if you're just looking at the aggregate, so you create features of eye tracking, such as how many times do you look between two representations within the problem, how many times do you look between the representation and the problem interaction, etc. And surprisingly, we found a negative correlation to problem performance, negative 0.6, in terms of students looking between graphical representations. So one hypothesis would have been, oh, if you're looking between them, you're starting to generalize, what's behind each of them. But instead, the explanation seems to be, if you're looking between them a lot, it means you don't understand what's in common between them. So in work that was applied to this at the 60 hertz, actually this should be 30 hertz level, using recurrent neural networks, what we tried to do was see if we could predict that same performance, but using the raw data, right? Every single eye position, 30 times a second, was the input, and then the output, whenever there was a problem answer, was a probability that it was correct, and how well do we do at this? So a neural network is RNN is kind of similar to word-to-vec, except it's only concerned with what's happening next, not the context, and it's also stateful. So it has some memory of everything it's seen beforehand, whereas the word-to-vec model does not have a state. It's just the input word and the context being predicted. So this didn't work out. We did not predict the probability of correct better than baseline using this data. Now, one explanation could be that, and this was 50 million eye tracking actions across 114 students. One explanation could be that this biological sensor level, people are just too idiosyncratic at that level to find generality between them. I certainly can't make the claim that that is the correct hypothesis, because we also observed a lot of noise in these data. And that is a kind of reoccurring thing that I've observed with a lot of biological sensor data, is they're often misaligned, or some correction was applied by the researcher, but you didn't get the correction code, so you're still working with the raw data. When we plotted the heat map of eye gaze for every student, they did not fit within the same window, and so that's kind of a red flag. So difficult stuff, but tantalizing, right? Oh, there's got to be some signal here. Really hard. Okay. And lastly is our favorite MITP. And we have a paper that was just published at User Modeling and Adaptive Personalization Conference. And this is the kind of data we have at 30 or 60 hertz for MITP.
Should be 60.
60, okay, that's the 61. The eye tracking was 30. So we have left and right finger height. So you don't need the X. Yes, thank you. You don't need the X dimension. You just need the height of each finger. So we have that 60 times a second. And then we have expert taggers who have categorized what strategy they believe was being employed during that segment. So A per B is the stepwise strategy of turning the screen green. And then speed is in response to the prompt, can you keep the screen green moving both hands? And achieving that is the speed category. Okay, so what are we trying to do here? We had 596,000 rows of that telemetry annotated for 5 users. So another difficult thing with these high frequency sensors is you can't get the same data set size as you can from popular online STEM platforms, right? Because these devices cost money. Often they need to be in a lab. So you end up with a smaller user count. But here are those strategies. There's also D, which is drag with one hand, keeping one hand still, exploring with the other. And again, we use the RNN methodology here, where we have the 60 hertz a second left finger, right finger data. And then at every time slice, so every one of those 60 hertz, we're predicting that label that the expert gave. So those are the hand labels. This is the 60 hertz touchscreen data. And you could ask the same question here. Is behavior too idiosyncratic at this level to predict labels for one student based on learning from the other 4 students? And I think probably not, because the hand coders were able to achieve reasonable inter-rater reliability in doing just that task, saying we've agreed on what looks like A per B, what looks like speed, what looks like drag. So it should be in the data, even though it might be very noisy. So how well were we able to predict that label? We tried a lot of different cross-validations, so having students held out and predicted, having sequences that were cut up held out, so you could learn about a student that you were also testing on. And we tried different ways of cutting up the sequence, cutting it up by contiguous labels, would each be a sequence. Right, this is a contiguous series of labels that could be defined as a sequence. Another sequence could be the prompt, right? You're prompted, okay, keep the screen green by moving both hands. All the data that happens after that could be a separate sequence. So the best results we saw was cross-validated by student and then cutting by sequence, and the baseline accuracy of predicting just one of these 3 labels was 66.6. So there was a dominant label that occurred that many times. And our model got 86.7. And then if you cross-validate by sequence, then partitioning by prompt is beneficial. You get 73% accuracy baseline and 89.8 with the LSTM. So still not great, but beating baseline when it comes to this high-density data is publishable. I mean, it's a reason to say, okay, this is what we did to get that. And the last slide here. But are there emergent behavioral regularities that can be surfaced from these data? So for example, Dor and his team have come up with those 3 strategies and some other as characterizing behavior in MITP, but maybe it's an incomplete characterization, right? Or in that maybe there's other labels, or maybe one label is too broad and should be split. So can we look at the data and see something that suggests that? So very much like what Scott did, we visualized the state of every student using the system at every second. And then we colored that state by the strategy that was labeled by the experts. So you see this space of strategies and how they manifest. So the dimensionality reduction was not done with PCA, because you usually don't get nicely structured representations when doing PCA on neural networks. We use something that, of course, Hinton came up with called T-stochastic neighborhood embedding, which is a nonlinear dimensionality reduction. And you see things like A per B has a cluster here, but then in some behaviors, that very similar behavior manifests as, drag, and then similar behavior manifests as A per B, which makes a little bit of sense in terms of the raters, right? You do have to drag in order to do A per B. So sometimes that can be confused or very similar to one another. So we don't have any big conclusions from this plot, but I have questions, such as what's the correspondence between this structure and one learned not from enactment? So our unsigned consenting participant yesterday in the MITP program, he knows proportion, right? But nevertheless, he still went through the same stages, right, of learning how to do the ratio test. Now, is it the case that because he knows proportion, he's got greater fluency in that task? So are they completely separate spaces, structures? That's probably not the case. They probably inform each other in some way, but in what way? Is it differential learning, the way that Michael's co-presenter, what was your name?
Claudia.
Claudia, thank you. Mentioned differential learning, right? Is it analogous, where this enacted, created structure is kind of like the primary elements that help you make sense of the semantic space? To be continued. All right, thank you.
Could you explain this last picture a little bit?
Okay.
It's beautiful. But,
Dor made t-shirts of it, he thought so much of it.
Actually did.
I don't know why he's not wearing it right now. But. Okay, sure. So let me go back to the RNN here. So this neural network takes as input the touch screen data, and then that touch screen data gets embedded as a vector here, and that vector is used to predict the label. And then that vector essentially is kind of like a prior for the next step, right? Which gets added in with the embedding of this vector. So we're not plotting every time slice, because then that would be too much. But we're plotting one. We're taking the vector every 60 time slices. Okay. Yeah. So every 60 time slices we extract this vector, and then we do dimensionality reduction on that vector. But the dimensionality reduction technique is one specifically designed for neural networks called t-SNE into 2 dimensions. And then we color that plot point by the expert label of strategy at that time. And that's what produces.
I thought that perhaps just to add a bit of context, I'll explain why we wanted these data. And in fact, possibly in the coffee break we'll soon have, or a bit later, we plan to bring back that large screen here more centrally. And what we've been developing in collaboration with Michael Neff from UC Davis is a teacher, an artificially intelligent pedagogical avatar. This teacher, whom we call Maria, who lives inside the computer and interacts with the child. So, as Tom was describing yesterday, part of our work where I actually worked hold the child's hands, perhaps, or I enact one of the hands while the child enacts the other, or just watching the child and giving comments. We are now able to do that without a human present. We're developing this artificially intelligent teacher who lives inside the computer and reacts to the very motion, the movements of the child by, for example, giving hints as to try looking higher or try looking lower, or maybe do that again, or have you considered this or that. So ultimately the idea is that we certainly want to expand this work beyond having to have a teacher work with every child, right? That's not the best use of this technology. So ultimately the idea is that any child who has an interactive platform like a tablet at their fingertips can interact with this embedded teacher. However, what we've learned over the years is that the way that teachers gesture is really important and more for understanding mathematics, and moreover for understanding enacted mathematics, to explain what you might do, how you might try to do things. And so these data were gathered in the context of understanding what it is that human tutors do as they make sense of what students are doing. And once we have those labels down, we can potentially have the software detect what it is the students are doing, so that the software can then respond in the way that the human would respond. When we built this pedagogical avatar, whom we call Maria, we took actually my gestures as I work with children and had Virginia put on a motion capture suit like they use in Pixar, and then reenact those gestures, capture them in fabulous ways that Virginia cataloged, and then we had the voice of someone else, of Alice, speak what Maria is saying, and all of that is now in a bundle that we hope to show you soon. Maria responds to students, and so it's my gestures reenacted by Virginia with Alice's voice. We have this pedagogical avatar that's interacting with students. So that's the reason. That's why we brought in the Marines. We brought in the learning analytics here to try and determine how we can characterize the human sense-making of children's actions in terms of the pedagogical responses we should be giving. So that's some context for this work. And Dan, I think you had it.
Yeah, no, so just that last description, I just wondered, when you move in that direction, I just wonder whether you were also undercutting the power of the interactions with other real individuals, right? So one of the things that you might want to think about is the social context and how we are geared up to respond to. I mean, that's quite a disembodied verb. You're going to capture some of the elements of the responses and the analysis, but also an avatar, right? It's not a real individual. I wonder what that will have as an effect on the learner.
Well, I would say that any person, any child who's working with, never mind cognitive tutors, but just any app, like math learning app, already they are, in a sense, they are isolated just with the app. So in fact, we are enhancing the app with humanoid or artificially intelligent capabilities, where the idea is that we cannot have a teacher, a real human tutor, work with every child at every moment, everywhere in the world.
Sure.
So rather by introducing that inside. So rather than think of it as undercutting, I dare say, on the contrary, we're imbuing this application with human-like communicative potentialities.
That could be examined experimentally to see what's lost.
That's what I was thinking. Yeah.
Well, yeah.
Or
to
to see if
of
anything
any-
is lost. Okay,
Yeah.
to see if anything is lost.
Exactly.
I mean, there is a field of virtual pedagogical agents, that's been pretty active in the
Sure.
past.
I mean, in the 80s, we used to have a paperclip.
The canonical, yeah. There's some things to watch out for. There was a study done where they tried manipulating the race and gender of the virtual pedagogical agent to match the user. And the condition where they matched them, performance was lower. They thought it increased engagement or relation to the tutor, but it actually served as a distraction of sorts.
Scott, do you remember whether there are differences in the optical couplings between two actors as opposed to an actor and a simulation or just a dot?
Yeah, the variability is reduced when there's a real person relative to, say, just the motion of an inanimate object.
Yeah, so it is acting as a visual metronome.
The stability of the
Yeah.
coordination is compromised, but it's small.
It's small.
Small.
Any other questions? Thomas and Scott?
I'm just thinking of an instance we had. It was a problem that the kids were working on, and it was share 2 pizzas among 3 people. And we had one example, the person cut them each in half. And then on the last one, they had two lines as well. It turns out when we examined, she had made an X. And so we went back and interviewed her, and she said, well, the way we do it at home is we each get a half, and then Mom puts the rest in the fridge. When looking at what she had drawn, it was an X on that piece, but the X kind of went over the edge of her cut, and we thought, well, wow, isn't it interesting that she's tried a third of a half, which would then be a sixth added to a half, and wow. And she was not a very good student at all, which she had this wonderful strategy. When we shared we share it as best we can, and then my mother puts the rest in the fridge.
That's funny.
Zach, yesterday, and I guess the overall coordination dynamics of learning, we put a big emphasis on trying to pick up intrinsic tendencies or pre-existing tendencies of the learner, and with the idea that that's what you modify when you learn. How would and we've talked about this also with respect to the ratio or proportion in learning and so on, that there seem to be certain actions that the child makes that may be useful in predicting the ultimate performance. How would you bring that into this, that sort of, I'm not going to use the word prior, but I just used it, into your mind?
Yeah.
Yeah.
So right. So let's say, for the purposes of answering your question, that RNN is a learner, right? And the weights represent their representation of the world, which is the embedding of that space into another space, right? This representational space. And let's say part of what gets modified is their model of how the system works, right? So, and part of that is how they anticipate what's coming next. So, in terms of, if you're asking what's the mechanism by which a modification to the learner is made that produces different behavior longitudinally, it's a changing of those weights of that representation. You know, that's what would be the analogy with the model.
I guess I'm asking what the initial weights would be.
Yeah, I think that's a fascinating question to me. So, literally in this model, it's random. You know, you start in a random place and you converge somewhere.
And I have to argue that it ain't random.
You know, I mean, DNA or whatever else. But I think it's fascinating to think of the interaction with those priors that may lead different learners to converge to different strategies, right? Not all use that attentional anchor, they use something else. So wherever you started with, everyone may learn to do the task, right? But they have different representations, maybe as a function of their prior.
The nature of the change, how it changes.
I guess that was the point of the example that I used, is the child has an idea. When we share, mom puts, does it easily and then puts the rest away. In other words, dividing it up equally just means that everybody gets an equal share, but it doesn't, an equal share of the whole. It isn't that, and I think there's, you know, it's a good example. What kids bring to the thing, you think, well, either you think, wow, they're doing this well, or wow, this is crazy. But,
Yeah.
you know, I think that's a real.
So I can relate that to the misconception analysis,
Yeah.
where it's disaggregating wrong answers, right? Like by different categories in which you got it wrong, different procedures you may have followed. I don't know how we would do it, but what you're suggesting is doing that to right answers, disaggregate right answers, right? But you know, from just the data of how you answered, we couldn't do that in this task.
That kind of relates, is the question of the norms, right? So you're talking here about the right, wrong answers against what, I guess here you set a standard view about mathematical norms that we've established for those answers. I guess that question was, you know, depending upon your background, you might shift your view about what's a right or wrong answer for context. I mean, you're holding them steady throughout the whole study, as if those were, you know, as if they were going to be right answers to those tabular questions and the relations. So where do those norms come from?
Like grading rubrics, or?
Yeah, I suppose so. Yeah. No, but I suppose in a lot of those cases, what goes together on what determines the definitive answer to these questions.
Well, in many ways, we don't have to grapple with that because we learn from all answers except for actually, this one also includes the right answer. So it,
Yeah, but the notion of the right answer is
Uh-huh.
article, right? That's one of the, that's in the background here too. It's not been explained as to how we decided which way. I mean, in maths, usually not a big question.
Uh-huh.
Some of the other ones you have your mix of philosophy and maths to get your physics example.
Ye-
You know, there are a lot of other questions here we could question what's the right answer about any of those.
Yeah, well then there's a higher order objective, right? What does the learner want to accomplish? And that's something we're trying to figure out. What are the...
It gets very nasty when I ask the normal question, but I thought I'd ask it.
No, it's a great one, especially because in the course recommendation case, it's probably just by itself rather useless to recommend what the average thing is, right? Because that doesn't correspond to anyone's intention. Point.
You had mentioned with respect to one of the examples, you weren't going to hold it against us for not getting it right because there wasn't enough information or we couldn't see the answer. And I'm wondering what it means to provide enough information for the learner to solve a problem. So is that an educational decision? I'm thinking back of the old-time criticisms, I think by the Gestaltists of Thorndike and the instrumental learning guys. So the instrumental learning guys said the animals they learned by trial and error. And the criticism was they had to learn by trial and error because the solution was not visible to the learner. So once you make the solution visible, then they have the insight and they can learn. So in this context, are there guidelines for how much information to provide to make the solution visible to the learner as opposed to just giving it away?
Yeah. Which context do you have in mind right now?
Well, so the one you had, the principle of you had the 5 rows of 3 triangles and the different pairs of...
Okay, the problem solving.
Yes, yeah, so should the solution... So you said the solution was not visible to us.
Oh, okay. Let me answer your literal question and then answer a different theoretical question, a big question. So the answer to your question is that the information was there, it just wasn't legible because of the size of the screen. So that's why I forgave you for that. I could barely read what the student answered. Yeah.
That became a big question.
Yeah, so that becomes a big question is, what information needs to be present to a student to even find a solution? And that's something that I did think about with the MITP, with a version that wasn't shown, which is where you see a gradient, right? It doesn't just change from green to not green. It's a gradient, right? So does that... So that's extra information. Can that be a crutch too, where they don't have to generate this attentional anchor if you can just follow that gradient instead? But these models need a gradient. So they could not work on this. It's right, now it's not right. It has to say, what's your distance from right?
Yeah.
It's interesting that if one changes the task constraint there by requiring students to move faster, then they don't have time to make the little adjustments. And that's, in fact, as we see sometimes, a child who has done that for a long time, certain aspects or certain properties of this dynamic transformation are not evident for them. And as Tom mentioned yesterday, there's the case where I literally come from next to a student and lift her arms this way, and for the first time, even though she's been doing the green, her arms are moving now a bit faster, and suddenly she says, "Oh, this one is it's moving double as fast as that one." Or those kinds of insights that became affordable because she couldn't have otherwise overcome the particular task constraint, that particular property of the speed.
And smoothness.
Go ahead.
So I just want another question, kind of relates, is the, again, framing effects. So it's not quite the prior knowledge, but the question of the way you frame and the familiarity with the task settings. So in a lot of cases, I think there's a good strong insight kind of work where, a lot of questions for kids, it's actually being familiar with the form of the question and what the question wants from you. More so than, so it's not quite, it's background knowledge, not about the structure of what's being asked. It can make a huge difference to performance. So being accustomed to thinking, what the norms there again kick in to say, like, what would I normally, why would you be asking this question, or what's the nature of the question itself? How does that figure into this?
Into this analysis, It doesn't. So all I can do is recognize that as a factor. Assessments, which is a similar system that I've done analyses on, it has a scaffolding strategy, and this came up in my class, a suggestion that that scaffolding strategy could be a little bit of a crutch, where when you leave that, then maybe you are missing the skill of knowing how to decompose a task. So there's certainly implicit pedagogical issues in these pedagogies.
I think this is a good time. Thanks, Zach, again.